This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Do we have a microphone? Yeah. We do. Are we in the right place? Am I in the right place? I hope so. Welcome to ELAN 90066, Embedded System Design. My name's Gavin. I'm going to be your lecturer for the semester. You may have had me in such subjects as ESD2 or ADEC before. If you haven't, welcome to the uni if it's your first semester here. Put up your hand if it's your first semester at the uni, if you're in the Masters of Eng. Only a few of you. Okay, so most of you are old hands at this. If you don't know me, I'm from Department of Electrical and Electronic Engineering, and my room's on the 3rd floor of the building. Okay, so what's this subject all about? If you want, you can read the coloured words and that will tell you what it's all about. The subject's about design, implementation, testing and documentation of embedded systems, basically, and the concepts behind them. It is a project-based subject in that there is a project that will underpin all of the semester, and then the lectures will cover theory that's related to the project as we go. Okay, so today we're just going to go over an overview of the subject. I'm going to talk about the schedule of how we're going to run things, then go into the mechanics of the assessment, because that's important. Talk about workshops, talk about assignments, the project itself, what is it? The exam, that's only a brief bit. And finally, we'll finish up with feedback from last year to show you improvements that have made, comments that were taken on board, things that people liked about the subject, etc. Okay, so we'll do the official bit, I guess, that the topics that we'll be covering are interfacing to the real world, and the real world's an analog world, so we're going to be talking about analog digital conversion, sensors, and going the other way as well, digital to analog conversion. And we're going to find that that's a non-trivial task. And a lot of the things you might have seen in existing subjects, DSD, so digital design, even ADEC or ENAD, even programming subjects you may have done, you'll find that a lot of the assumptions that you've been living under are false when it comes to the real world. Example microprocessor architecture, so you may know a little bit about programming but not necessarily understand what happens when you run a program. You might know how to write a program, but we're going to talk about microprocessor architectures. Then we're going up high level stuff like operating systems. So what does it mean to be multitasking or run tasks in parallel or concurrently? So these are interesting things that happen all the time on machines and embedded systems, but you might not know the concept behind it. And system level programming in C, and that's just the standard that people use to program these days. So if you haven't had any experience with C, you might have to start reading up on some of that stuff. If you've forgotten it, go back over it. It really is a basic language to learn. So underneath all of this, it's not just all about the theory. You are going to be exposed to numerous software tools. Okay, those tools are tools to program embedded systems, debug embedded systems, and get data back from embedded systems. And we're going to provide you with a range of different ways of doing that. There's more than one way of solving a problem. There's more than one tool that does the task. So if you like programming in C, there's a way to deal with embedded systems programming in C. If you like more abstract way of graphically programming things called model-based design, you can use LabVIEW. Okay, so there's multiple ways of doing this. Compilers, debuggers, etc. The intended learning outcomes. So once you come out of this subject, hopefully you can understand about designing, building and testing, in particular a real-world embedded system project. You can develop, test, experiment, document, all that sort of stuff. And, well, the project underpins it all. More on the project later. So, lectures. Obviously, you're here for 9 a.m. We have a 5:15 lecture as well. We kind of get a bit, I don't know, shafted by the lecture times. So, trust me, I didn't ask for these times. Got given them. And when I got up at 5:30 this morning and I felt like death, as you can tell, I've almost lost my voice, I thought, embedded systems, lecture 1, 9 a.m., go back to sleep. Call in sick. Embedded systems, sleep. And I thought, oh, I'll come here. So I chose you over my health. I'll probably regret it by the end of the day. Okay, so all lecture slides will be posted to LMS. Please note that it's a new subject for this semester. It is new. So that means lecture notes will be posted as we go, normally about a week in advance, hopefully. But we have a big textbook that everything's based on. So the lecture slides are really just a summary of the relevant chapters of the book with examples and discussions as we go, okay, and some cool videos and all that sort of stuff. All right, so don't be sitting there saying, oh, the lectures for next week aren't out, I can't do any pre-reading. The book chapters are all there. The book tells you a lot more than the slides will. The slides are there to guide you, and we have discussions and etc. Okay, so everything comes through the LMS, etc. My consultation time is Wednesday, 2 p.m. So, this subject has a textbook. Textbook's called Introduction to Embedded Systems, a Cyber-Physical Systems Approach. It is a fantastic textbook. The textbook is here. Ooh, it's really nice. It's not hardcover. It's a nice, zoomed in. It's a nice size and it's got lots of pages and stuff, right? You can get it online, Amazon, wherever. But the best thing is, it's free, legally free to download. Yeah, I know you can get a lot of textbooks for free, but where some poor buggers scanned in the pages. But this is available online, and that's fantastic because it's obviously beautiful. You can get high-resolution images and all of that stuff, but it's also searchable as well. So you can just Control F to find terms and such in there. So that's fantastic that it's free. So what the textbook does is it identifies and introduces durable intellectual ideas. I love how it quotes that, of embedded systems as a technology. We'll find out that there's a lot of hype about embedded systems. There's a lot of rubbish out there. It's important that we durably and robustly study how embedded systems work, not just talk about fluff and that sort of stuff. Okay, so we need to have provable ways of showing reliability, reachability, such things that embedded systems must demonstrate. Not just kind of say, oh yeah, I think it'll work. Because these systems underpin a lot of everything that we do, and safety, relying on safety and such. Okay, so if you notice on the little textbook cover here, there's 3 bubbles: modelling, design and analysis. And that's how this course is structured, and it's also how the textbook is structured. And if you look in chapter 1, or the forward, I think, of the textbook, it gives this beautiful diagram showing you how the book relates to all of these 3 areas. Modelling on the left, in the middle design, and on the right analysis. And there are dependencies between the chapters. Now, the idea behind the book is it's not a front-to-back book. Start at chapter 1, go chapter 2, go chapter 3. That you can read stuff concurrently as you go, okay? So the arrows are trying to show you, you might need something before you read something else, but other than that, you can read it all at once in one big blob. And indeed, we're not going to go from chapter 1 through to chapter 17. We're going to start at 7 and come back to 2, okay? Because we need that for the workshops, right? So I've also put up the lecture schedule on LMS, and it's colour-coded to the chapters of the book as well. And that's what those numbers mean there. So the numbers are going to be the textbook chapters that we're looking at. Some chapters we're not going to cover everything for. For instance, synchronous reactive models is only a part of chapter 6. So this is your guide, and I colour-matched these things with the eyedropper tool in PowerPoint or whatever this was, and made sure it's all nice. Now, workshops, as you'll see, we don't start workshops till week 3, but for those of you in Friday classes, you're starting week 2, and this got cut off. So week 2, because we lose a Friday somewhere down here, in this week here, we lose a Friday, there's a public holiday. So we lose the Friday workshops. Luckily, we don't lose a lecture. All right. And there's a bit of a hint with what the project is. You can see some sort of interfacing sensors and stuff, and then some sort of sea and hill climb and navigation robot. So we'll see a bit more about that in a minute. Okay. So let's talk about the assessment, because the assessment, well, is going to point to what the project's all about. This is the easy one. There's an exam in the subject. It's 60%. It's a hurdle. You must pass the exam to pass the subject. Leave it at that. And what I'm going to do here is put all these bits together, and I'm sure we can all add 60 and 40, or subtract 60 from 100 and work out that it's 40. But 40% of the assessment is about essentially the project, really. 20% of the assessment is going to be a final report on the project that you do in your team. So it's a team-based final report. And it's going to be submitted after SWOTVAC. So first day of the exam period, after you've done everything, you've done your demonstration, etc. More about the project in a minute. But as you're going during the semester, you're going to be completing workshop tasks that will support the project. Okay, so you can almost add that 10% on to the 20%, really, because you're going to be marked for very simple tasks in the workshops, achieving a certain goal in each workshop, and then moving on. And that is leading you towards completing the project. There are 6 assessed workshops, and then there are some that are not assessed, which we'll see in a minute. There are pre-labs as well to be done, and I want everyone to be doing them individually. Okay? The problem with project-based subjects is if you're in a team, people can freeload off you, or you could freeload off other people. Hopefully you're the former, not the latter, right? So I want everyone to be at the same standard. Do your pre-labs. Everyone knows what's going to happen in the lab, and you're going to work together well as a team. Everything's submitted through LMS as well. Lastly, 10%, there are some assignments. Now, you need feedback. Workshops are great. You rock up, you do your 3 hours of workshop, and you get a bit of feedback, and then you get nothing for the next week. Or you get the feedback in a team context. It's a bit murky as to maybe how much you really know. So the idea is that there are 3 assignments to be done individually during the semester that will really be more of the theoretical side of stuff. Okay, so you're doing the practical stuff in the workshops, but right, this is exam prep, basically. These assignments giving you individual feedback, not hiding you in a group and you're going to think you're going to do well, but you've been copying. Okay, so that's what that's all about. So that 40%, and it's based, that has application to the project anyway, that 10%. Oh, I'm dying here. Okay, so there is a lab manual also for the subject, and it's available online. I've put it up on the LMS as well. All our workshops will refer to this lab manual. It's pretty good. It's comprehensive, but it does have some mistakes in it. Trust me, I've found most of them. So there will be some additional materials on LMS which will supersede what is in here. So you're going to be following this. It's about 250 pages, so don't print it out. It's a PDF. You can view it online or on a mobile device or whatever. And there will be some slides that will be available before the workshops telling you specific things that may need to be changed in the instructions. Okay? And also telling you which tasks to do for assessment in the classes. So just to give you an example, if you haven't been to the workshop class, the workshop part of the LMS, you'll see here there's two versions of the lab manual. There's one with all these other supporting documents. There's a few research papers and things to read in there, bundled up as one file. But if you want to view things on, say, a mobile device or something, there's one version of the PDF with links that go out to the other files. Okay, so this is all the files bundled together, and this is just the one file with external links. Okay, once again, it's over 250 pages long, and not all of it's relevant anyway. There are chapters which we're not going to be using in that, but we're going to be using 3 or 4 chapters out of it. Now, one other last thing I forgot to mention. Where is it here? Somewhere. Ah, here. So if you're new to the uni, and some of you are, please note that you must complete the occupational health and safety online training thing, if I may call it that. It's fairly simple to do. Instructions will come out soonish, before the first workshops anyway. It doesn't take long to complete. Is there a whistling noise or something? Did anyone hear it? My ears are totally blocked, so I can't hear a thing. But I did hear something. Okay, so if you've already completed in semester 1 for another subject, hey, you don't need to do it again, so that's all good. Details will come out. Don't go looking online for online courses and stuff like that. Just follow a link that will get sent to you. Don't try and preempt things. I know you're trying to be good, but don't be good. Yeah, you know what I mean. Okay, so what's the assessment in the workshops? There is 10% total assessment in the workshops. It's a 3-hour class. You have more workshop time than lecture time, and that's what it's about. It's about practical skills. Workshops start Friday of week 2. I've said all that. The workshop schedule will be coming on LMS soon. A more detailed one telling you all the pre-lab exercises you have to do for the rest of the workshops and what exercises are assessed in each workshop. Okay, so you're going to give you a complete roadmap of the rest of the semester. They'll go up today or tomorrow if I'm alive. So there are 6 workshops where it's going to be called loosely Learning the Tools. And it's pretty much hold your hand. This is new stuff to you. You're going to be learning stuff you've never seen before. And, you know, smashing your head against the table as things go wrong and learning to get around all that stuff. So you're guided. It's like the steps are do this, do that, look at the results. Okay? So you're progressively building up your skills as we hold your hand for the first 6 workshops. There's individual pre-lab work. You've got to get that submitted 8 a.m. on the day of your workshop, by 8 a.m. Okay, which really means do it the night before, the day before. Then there are these numerous in-class tasks that to be checked off as you go. And it's really as simple as, did you get to this? Show us what you've done. Explain what you've done. Tick. Okay? That's what it's about, the in-class assessment. It's about you getting competency, not sort of, oh, you get 6 out of 10 for that and 8 out of 11 for something else. It's more just about tick. You get to that stage, move on. Okay? It's competency. Then we take the hand away. And workshops 7 to 9 and 10, really, you're on your own. You can come to the workshop class if you want, or you don't have to. You are going to complete the project. So learning all the tools, taking you through a structured way, you're then going to be redesigning, experimenting, optimising your solution to the project, documenting your design and testing procedure. There are no pre-lab exercises and there are no in-class assessments. Okay? You're on your own. Use that time as you best see fit. If you already finished the project, good on you. You don't have to go to those classes. And then workshop 10, you must be there for the grand finale, and that's a demonstration of your final project solution and a bit of a competition and such. Okay, so the final project report, it's 20% of the total assessment. Now, you completed your teams, that's obvious, but what I want to do is, this subject is a prerequisite for the capstone subject, if you're a mechatronics or electrical student. And the idea behind this subject is to gear you to be ready to do the capstone project. So think of this report as a mini capstone report. Often we get capstone project students, I do anyway, that have no idea how to write a report. They don't even know how to structure a report. So this is your practice. So that when you get into the capstone next year, you know, you're going to smash it, basically, okay? You're going to know exactly how to do a report. So it's about documenting theory, design process, your testing, your outcome, a discussion, bang, you're done, get it in, and you're laughing. More details will be provided on LMS. We're going to mark it a very similar way to the capstone project report, obviously scaled down. It's not 80 pages or whatever. It's going to be much smaller. But the idea is to give you a practice how to get graded according to a capstone report, which is good. So what is the project? Well, I have the project with me here in the bag already. It's missing its brain, but this is the project. This guy here. A kabuki robot. Robot vacuum cleaner, you might want to call it. It doesn't have the sucky part on it to suck stuff up. It has the motors, rotary encoders, you can read angles. It has bump sensors, 3 on the front. It has cliff edge sensors that can detect if there's a big drop. It has, as you'll learn, you're going to interface a 3-axis accelerometer on here so it can tell when it's on an incline or not. Now, I'm just going to leave this guy go for a bit of a random walk. Why not? So this has a basic program in him now, which is just going to keep driving at 50% speed or something like that until it encounters an obstacle, which then it will turn a random angle and then proceed forwards. And it's hit a circular... Oh no, that's all right. It hit a circular obstacle, so it kind of went around it. But every time it hits an obstacle, it will, as I said, rotate a random angle and move onwards. Ugh. So it's pretty dumb. But, and I'll just show you again. Right, so you might think that's fairly simple. It's not that simple, particularly when you have to think about ramps are involved. And your goal is going to be to get this guy around an obstacle course where there are some static objects in the field, and there's also a ramp which you must detect that it's on an incline, climb it successfully, get to the top, etc. No crashes allowed, no falling off the edge, and do it as quickly as possible. Okay, so that's a bit of fun. Where did it go? Okay. So, as I said, it's in the dumb mode at the moment because it doesn't take into account any of its sensor readings, really. Okay, so as I said, you have assignments that you'll be doing, and this is to test your theoretical knowledge. It's great to be able to be programming this guy and getting great results, but you've got to know the underlying theory. 3 assignments are spaced out, week 4, week 8, week 10. And then the last 2 weeks, you're concentrating on maybe getting your project ready, so I'm not going to be overloading with an assignment. And you submit them and get feedback through LMS. What are assignments there for? What are they really there for? They're for, yes, individual, good, but feedback. They're not there for me or the demonstrators to mark because we like marking them. We don't. If it was my choice, I'd give you no assignments, right? You maybe be happy with that. But you need feedback. You need to know how you're doing and, you know, test your knowledge before you go into the exam, particularly, right, if it's a 60% exam. Okay, so they're there for you. And then, of course, there is the final exam. So the final exam is a closed book exam. That's obvious. It's a hurdle requirement, which means you really should be doing those assignments. You're allowed to use approved calculators. And lastly, past exams, or you may have heard from some friends or family members or someone who's done this subject before, will be very different. So if you have an illegal copy of past exams, they're not going to help you. And I'll tell you a little bit about more where that's coming from in a minute when we talk about subject feedback. Okay. Do you have any questions? Any questions about the mechanics of the subject or anything like that?
Considering there's no past exam, what would you say is the best way to study for the exam?
Okay, there's a textbook with lots of example questions. There's assignments, and I might put together a practice exam for you guys to work through.
About the robot, will we only coding the robot, or do we have to build that robot as well from C?
No building. So you're going to be programming it, learning how to read its sensors, calibrate them, which is a very important thing, and then make decisions based on the sensors, right, via state machines or such, whatever you want to do. Okay, too much to be able to actually design that guy. Yeah.
Can we visit the size of the robots where we will play with it in week 10?
In week 10. You'll be given a map of the layout of the obstacle course, but we don't, and you'll be testing, so in workshops, let's go back a bit. In these workshops here, workshops 1 to 6, 5 and 6, you'll actually be testing with real obstacles and with a real ramp, okay? But not the course itself. One of the things we don't want is we don't want people a priori looking and saying, oh yeah, I'll just make it go forwards, turn left, turn right, and there's no sense of feedback, right? It just does it deterministically, right? So we don't want that. All right, so yes, you'll be able to practice in the rooms that you'll be doing the obstacle course on with the real obstacles, but you may not know the exact layout of what the obstacle course will be in the end. Okay? No other questions? Yep.
What kind of capstones does this subject lead into? Can you give us an idea?
With capstone projects, you basically look at a list of projects that are offered and you just apply for them in a preferential manner. So this subject will help with anything that involves embedded systems, microprocessors, robotic stuff. You'll see a little bit. We're going to talk about what cyber physical systems are in the next lecture, and that may give you a better picture about the experience that you get from this subject and how it'll help you maybe choose a capstone project in embedded systems. Okay, so I want to exactly talk about cyber physical systems. Now that's really what embedded systems are. So I'm going to be, as you notice, the textbook says, Introduction to Embedded Systems, a cyber physical systems approach. Now, isn't that a great term, cyber physical? It sounds futuristic and such. But that's what they are. And as I said, I'm going to dispel a lot of myths about this sort of stuff. So cyber, there's a computing part and a physical part. Most stuff now interacts with something that is physical, mechanical, normally, right? An actuator arm or something like that. Or even just sensors, right, that are detecting events, right? So there's a cyber and a physical side to things, which often we just split. We go and do a computer science subject and we just do the cyber part. I hack up a program in C. We don't think about how that's really going to be interacting with the physical side. Or you do a mechanics assignment and you think about, okay, Newton's laws and such, right? But you don't think about perhaps how that would be controlled by a computer necessarily. Okay? So you've got to think about computation on one side and dynamics on the other. That's interesting. It's a really interesting blend. And cyber physical systems is an area that's just going nuts at the moment, as you'll see, with the so-called Internet of Things, which is a term I really hate. Security and safety is also part of the package as well. So automotive, energy, biomedical, avionics, military, manufacturing, buildings. These are all examples of cyber physical systems. There's an underlying computational part, and then there is a physics, if you like, or physical system that is being interacted with. And this leads to some very, very important questions. There are contradictions inherent with this approach. Think about it. Adaptability versus repeatability. Do you build an embedded system that is very good at doing one thing and one thing only, but if something goes outside the parameters of what that's used to dealing with, it just loses it? Or can it be a bit adaptable? Sensor values go out of range. Oh, okay, I'll just ignore them. Or does it rigidly follow those sensor values? Adaptability versus repeatability. High connectivity versus security and privacy. Right, do you want to make things that are, think wireless, easy to connect to, get into, or so adoptable by a lot of people or different devices, or do you want to just lock it down? One type of hardware and one type of hardware only can connect to it, and you've got to go through certificates and encryption and all that sort of stuff. Immediately then you cut down the amount of people, for instance, that could access a particular system like this. That's interesting. High performance versus low energy. That's a fairly obvious one, right? The more performance you need or you want, then obviously the more power you require. Embedded systems are typically very low power because we tend to put a battery in it normally, and if it's a remote sensor or something like that, right, it sits up somewhere out of reach and we don't want to be changing the batteries all the time. So we normally would go with low energy for that. Asynchrony versus coordination or cooperation. Do you want these devices to be working independently almost, right? Not at some fixed interval? Or do you want them to cooperatively behave somehow? Now, looking at that manufacturing example, right, where there may be more than one robot acting on that car at the same time, they've got to be coordinated. They've got to be synchronized somehow, right? They can't just do stuff when they feel like it. But there are cases where we have cyber-physical systems where it doesn't matter. Things can happen out of order. It doesn't matter. Scalability versus reliability and predictability. Has anyone heard of the acronym MTBF? MTBF. I'll write it down. My damn tablet. MTBF, mean time between failures. When you put a product to market, you normally will have to quote the mean time between a failure of the device. And that gives an estimate on, how long it will be before it fails. And that is related to, obviously, how well it's put together, but it's also related to how many units are out there, right? If you have a mean time between failure of a certain amount, but then you pump a lot of those units out there, you think statistically, okay, there's the mean, right? It might be normally distributed, right? Where the mean time between failures is some point. But the more you get out there, the more likely some will fail early. Okay, so we have scalability. You start pumping lots of stuff out there, your mean time between failures could go right down. Or do you just really restrict it and only put a few out there and you can live with perhaps no failures or very predictable behaviour? This is a good one. This is something you have to think about as well. Laws, yes, and regulations versus technical possibilities. There are things out there that we can do right now that we're not allowed to do because people say, you can't experiment on humans and such things like that, privacy concerns. And that's an interesting world we have to live in as engineers. Maybe other professions don't have to think so much about that sort of stuff. They can just sit in their labs and do their little chemical experiments and such. But we actually have to think about the technical possibilities and how they fit in the framework of laws. Economies of scale. So the cloud, I'm sure you're familiar with that, is like, Internet of Things, this sort of stuff. That's worldwide versus, say, something that's local. And we call the local cloud, we call that the fog, right? So it's down low and it's just around. So do you want stuff to be, obviously, repeated worldwide and have that sort of scale, or just a local system? Open versus proprietary. This is a very interesting tack as well. Do you make a device where you say, hey, I'm putting this product to market, here you go, here's all the code. You guys go and take with it what you like? Or do you hold it back and say, all this stuff is locked down, it's encrypted or whatever, you cannot disassemble the code, And if you want updates, we give you updates, and that's basically, you can't do any modifications with it. Very different models, right? Algorithms versus dynamics. Algorithms are great. They can do anything you like. It's simulation world. But the dynamics of systems limit what can happen. I can make an algorithm that can make a crane arm move arbitrarily fast. But if I go and try and program that into a real crane, what's going to happen? It's just going to snap, okay? Because the dynamics of the system are such that it cannot react that quickly. Is there some high-pitched noise going on? There is? Okay. I couldn't tell if it was in my head. Right. Okay, so this is the thing. You guys are going to be the next generation of innovators, right? Our time is over. So it's up to you guys. Cyber-physical systems require these new engineering methods that think about all these contradictions all at once. And you need new engineering methods and models to address these contradictions. As I said, this is a hot topic at the moment. CPS, go and look it up, cyber-physical systems. Very hot topic. So here is some buzzwords. Internet of Everything, Smarter Planet, Machine to Machine, the fog, trillion sensors. Cyber-physical systems encapsulates all of this stuff, right? Embedded systems being cyber-physical systems, right? That guy up there, the thing you hear most of, Internet of Things. I hate that term. It's 3 words, and only one of them is a good word. Guess which word that one is? The of part. That's the only valid word there, right? As I'll tell you in the next lecture, internet already tells you TCP/IP, right? It's telling you a particular realization of something. Not all embedded systems use TCP/IP, right? Things. What's things? Things are sensors, devices. They're real, real elements that are interacting with the world. Things. It's so vague, but the media love it. So, but cyber-physical systems encapsulate all of this stuff here. And we're going to talk about more of that next lecture. We're going to give, I'm going to give you some examples about some real-world cyber-physical systems. And then I'm going to take one example and project it on the textbook and show you how that was developed according to basically the flow of the textbook. Okay, so that's your little motivator for cyber-physical systems. What I want to talk about is the motivator for this subject. Right? We can motivate cyber-physical systems all we like, but... So, this subject ran in a particular format for many years, and it's now changed for this year. Now, yeah, there's lots of reasons for the change. What can we say? It's time for it, right? It was getting outdated in terms of the project that was run and the way it was taught. So, how I restructured the subject is I restructured it looking at what the best aspects people thought of it was last year and highlighted those and got rid of some of the worst elements. So I'm going to show you real SES feedback from last year. Practical work. So students loved the practical side of things. Perfect. We've got some practical stuff for you guys to be doing where you can actually see your algorithms in action. You have more workshop time than lecture time. Isn't that a great thing? I mean, really, do you really need 3 one-hour lectures a week? You guys are independent enough. Subjects have been a blast. Working on a single project. That's the key. Single project, right? I know you'll be doing some other things with some other pieces of equipment, but that's in order to get experience with the tools. Right. Freedom to program whatever you wanted. That's going to be as well underlying under here. You're going to program whatever algorithm you want to get your robot around that obstacle course successfully, hopefully. Okay, so going into great detail, yes, we will go into great detail in the lectures, but it's about the application of the theory. So I'm going to be trying to relate this to real-world stuff. I'll tell you interesting stories. I'll tell you stuff about how things were developed. You might know the history behind some of the processes and things that you use in your machines, but it's a fascinating history. And it's a legacy. We have to deal with that stuff now. Stuff that was invented in 1980 is still a legacy now that we have to deal with, okay, when we're doing the embedded systems. Wow, you wouldn't think. Love doing the project. Okay, great. People love projects. Doing something practical, that's what it's about. Demonstrators are good. Hopefully I've got good ones again this semester. And again, someone else said the project had a good balance of having information, but also having to figure out things oneself. 6 workshops where we hold your hand and then we let you go and explore yourselves. Okay? That's what it's about. You get the most out of that if you do it that way. Okay. I had to put this one in here because I thought this was funny. So 12 months ago, I snapped my leg, and that was the week before semester. So I had to give lectures with a leg that was like still freshly broken, and it wasn't a particularly smart thing to do. Luckily, this year, I only have an absolutely terrible cold, so it's better, but I won't break a leg this year. Promise. I'm not playing soccer anymore, so I won't do that. Now, design, project, and learn C code. This student wanted to learn C code. That's great, because it's in the subject this time. So learn C code. Now, there's an alternative. If you don't like working at the C code level, you can program your robot with a model-based approach using LabVIEW. That's great as well. So we give you choice. The lecturer gave a good explanation of the important knowledge through a vivid description, a combination of many interesting cases. The curriculum of the practice project is very good to cover the knowledge that needs to be learned. It deepens my understanding of practical ability. Wow, it's almost like I wrote that myself, isn't it? I'm going to, steal that. The best aspects of the subject are its well-developed structure and iterative lab tasks. So once again, I've tried to carry that across into this new iteration of the subject, making sure that everything's well-structured. Right, and this is the best one. The practice is the beset. Not really sure what that means. I think that means bestest, or is that a word, bestest? I don't know. Okay, so what did people say needed improvement from the old version of the subject, if you like? The difficulty of the project was okay, but we were provided with a bit too much guidance. Very easy to complete it, so they said very easy, it was okay. They wanted more theory. All right, we're giving you theory. And less example code. Also, the marking scheme pretty much told us what we needed to get 100% in the project. So the marking scheme is very different from last year, firstly. More theory. Okay, they asked for it, you get it. That's how it works. Now you know, right? On the SES this year, I want more theory, I want it to be harder. And the next year it gets harder. No, it seriously needed a bit more theoretical backing. That's why we got a textbook. There was no textbook last year. So, these are my responses. Response, complete restructure of the subject. So, the student said, my JTAG doesn't work entirely. The tutor can program my JTAG, but I cannot program my game console via the JTAG. That is weird. I had to buy additional JTAG from eBay to program the game console. My response, sounds like it's you, right? Not JTAG. But there's no JTAG this time, so you get around that problem. I would have said to the student, it's you. Okay, what else did they say? Is it embedded system design? And why we have programming in that? Okay, they clearly don't understand embedded systems are, well, they're run by microprocessors or whatever that have programs on them. This subject is only about AVR. It's better to cover some knowledge of how to choose different MCU microcontrollers in practice. Okay, yes, the focus is on one particular type of AVR and its instruction set, which was very focused. This time around, we're going to be talking about many different families of MCUs. CISC processors, RISC processors, x86 architecture, lots of different stuff, okay? So it's not focused on one particular type. So that's good. That's better for you guys. Yeah. An AVR, proprietary microcontroller. This subject is not a subject name, reading data sheets to learn. Reading data sheets to learn. Tutor or lecturer should focus more on explaining data sheet, especially somewhere important in detail, because Gavin is teaching it with simple words which you might think we get it, and we might think we also get it, but actually those simple words did not help to understand the data sheet at all. It was really positive, but then they said they don't get it. Response, there's going to be no reading of data sheets, at least not to the extent that there was last year, okay, which you had to scan through a lot of stuff. You're going to have to read some data sheets. Of course, that's part and parcel of digital design and embedded systems, but it's not going to be about having to scan through a 100-page document looking up instruction sets, that sort of stuff. We're going to be working at a higher level. It's the C level or at the LabVIEW level of abstraction. Okay, so how are you going to do well in this subject? It's new, right? Stay current, that's the thing. Get the textbook, it's free. Download it, have it with you. Go over the lecture material, obviously. Reinforce after it's presented. If there's something one point that didn't make sense in the slides, it obviously relates to something in the book, and there'll be probably at least 2 paragraphs on that point. So that will give you a much better explanation than what one dot point can do, okay? Read the textbook, there it is. Use feedback. Feedback's important for you guys. Use feedback to assess your knowledge and guide your study. Often, and we did this when we used to have paper-based assignments, we would spend ages sitting there marking the assignments, writing comments on there, and we'd have a big box of uncollected assignments at the end of semester. And we put a lot of time into saying, you did this wrong, maybe perhaps do this, that's great, whatever. It was all wasted effort. So the feedback is there for you guys to take and read and learn from, or give yourself a pat on the back, whatever you want to do. But it's there for you. You'll get it electronically, so at least you'll probably read it this time. But please use that as, use it and act on it. Try to solve problems yourself. That's the obvious one. When you get into the exam, you're not going to be able to look at a question and ask the person around you how to do it, right, clearly. So have a go at the problems yourself. This subject is, once again, the whole area of cyber-physical systems is full of these inherent contradictions. It means you can be asking questions about, hey, why don't they do it a different way? Because maybe it makes sense to do it. Well, there's probably a reason why you can do it a different way, or you choose not to. That's going to be the exciting part of the subject. Okay, so you're going to be pumped full of resources, lecture slides, some worked examples I'll be putting up on LMS as we go to give you an example of the types of questions that might be asked. We've got a textbook. I'll point you to other really good books that are out there. Some are available in PDF format as well. Your notes from your workshop classes, feedback from assignments, talk to your demonstrators who are good people, and consultation sessions where you come and speak to me. Sorry, just made it. And next lecture, we're going to go into depth about what cyber-physical systems are and give you examples. We're going to dispel this whole Internet of Things myth and frame the rest of the subject from next lecture. Okay, so I'll see you late on Wednesday if I'm still here. Yeah.
So I was wondering, for embedded systems for this course, is it necessary to understand registry programming, register programming, and stuff like that?
From a high level, from a fairly high level, knowing what a register is and that they're used to store results of things, and like an arithmetic logic unit, an ALU, can operate on those things. So you don't need to know necessarily assembler code or anything like that.
Yeah, because
it's too low level.
In my undergrad,
yes,
I did an embedded system paper, but it wasn't high level like this one. It was more low level, so that's why I was wondering.
Yeah, remember, this is looking at embedded not from a sort of, oh, here's a data sheet, you've got to learn to program an AVR with this instruction set. This is more about how do you robustly design an embedded system? How do you look at how to predict how it's going to work? That sort of stuff. Okay?
I'm here on a business, so wait. I'll let these guys finish first.
Yeah, who's next?
What are you asking?
Sorry, I can't hear you very well.
Right, I got
Level of C code you need. Is there a level of C? Is there a level? I don't know how you assess levels of C code. You need basic proficiency.
Like basic, like not high advanced.
Basic proficiency. You need to know how to call functions, do arithmetic operations, that sort of stuff.
Do you know Moffat's book? This is the workshop.
Do I know?
Moffat's book, Alistair Moffat.
I haven't seen
He's one
it.
of the lecturers here. He
I know
wrote
Alistair,
the
yeah.
textbook on him.
Yeah. I just know the
Is it free?
And it's not free, but it's cheap, and it's the only textbook I've ever bought.
Okay.
And I refer back to it every now and then.
Okay, there you
Pretty
go.
good.
There's one. Yeah. Look, you'll just see from the workshops. Start reading the text. There's snippets of code in the textbook, and if you're reading the bits of code going, I don't know how to do that, then that's when you start looking at it. Okay? I can't rate how tough the C code is. It's very hard to do that.
I just wondering, and what's the code here? Like, you just download the workshop code from LMS, but there's no code here.
Yes, there is. Oh no, sorry, I haven't released it yet. So there's going to be the code for all of the workshops up on LMS.
My last question is, I cannot find this in the university library.
Amazon.
I don't need to. I don't want to buy, so I just want to borrow it. So
It's not in the library. So why do you want to borrow it? Get a PDF of it and put it on an e-reader.
my eyes are not good, so I need to see like in paper, like.
Print it out.
Yeah.
That's about the only solution.
Okay, thank you.
All right.
Sir, so we need to download the C code and to understand all of it. And so that's all. So
Yep, I'll be putting the source code up very soon for the workshop. Okay, I just need to fix something.
is that all the knowledge we need to learn from the C? So the C code on the workshop.
Yes.
All the knowledge we need
Yes.
to know about C.
Yes.
And you don't get an Aussie source for the movies. I can only find them in
South Korea. Yeah.
okay.
No.
Yeah, okay, fair enough.
They're expensive too.
Oh, yeah? Maybe like
$500 US.
Oh, it was US. Okay, I thought it was like yen or something.
No.
Yeah, nah, not doing that.
No. You have plenty of time to play with them anyway.
Thank you.
I'm just wondering to what extent not all guys are the same, so need to go with things like dynamic differentiation, things like that.
Nice. Not that sort of stuff.
Okay, so just like basic kind of.
Statements. Yeah, how to call a function.
So
That sort of
basically
stuff.
any regular programming.
Yeah.
Specific C.
No.
Thank you, I hated this.
Very good.
Sorry, I
Yes.
missed the beginning of the lecture, so I just want do you have a workshop this week?
No.
From next week, right?
Friday.
From next week, right?
Friday next week.
Oh, okay.
If you're not on a Friday, week 3.
Okay, sure. Thank you.
Okay.
I was gonna ask what happened to the Game Boy project, but
Yeah, it died.
yeah, not fair enough.
How come?
I don't know, change of subject material.
Yep. So,
update it,
yeah, so I did try and elaborate about why the subject
Yeah.
changed. The subject was taught very much as a skills-based project, but skills that were not at the master's level. That's the nicest way of saying it. So learning how to solder and stuff like that. That's skills, great skills which you can go and learn.
yeah, online, some blog or something.
Or MUEC, for instance, run soldering workshops.
Yeah, no, I'm part of it, so.
There you go, right?
Anyway, that's not the why I'm here today. I've noticed that your ESD2 lectures on Wednesday, Thursday, and Fridays. Is that correct?
Yes.
Well, I'm here on the behalf of the Multiplex Committee. If you haven't heard, it's the gaming festival that MSC is supporting. We were wondering if we could lecture bash your Friday
Is this the one you guys say funding?
I think
I
so.
find it seems to be okay.
Oh,
with
wait.
me. Just have to have
I just want you to
your
know,
power.
alright, I was dragged to this, it was not my idea, but yeah. And we were hoping we could sort of lecture bash your Fridays, if it's possible. If you don't
Friday?
Sorry?
Yeah, we were gonna do Wednesday, but like we figured it's gonna be the first lecture, it's gonna be the intro. Yeah.
Friday is perfect because I've already got someone lecture bashing on Thursday.
So you have to insert them into your...
So one slide, if you want to
One
put a
slide.
up.
Can we do a website instead?
Sure. Yep. But I mean that's giving you a guide to the timer. if I say one slide, people think, oh, geez, that's like 2 minutes maximum of talk.
Oh no, that's fine. That's fine. We're just gonna go quickly and
Yep. All right.
last
Thank you very much.
Have I got everything?
Have you got everything?
So,
Is it all yours? Are your glasses?
no glasses.
And it's your USB? Yeah, that's